Everything you have ever touched, every surface your fingers have pressed against, every object you have ever held is made of atoms. And every atom has a size. But here is what almost nobody thinks about. An atom has no wall, no shell, no hard edge. There is nothing solid at the boundary of an atom. If you could somehow shrink yourself down and fly toward one, you would never hit a surface. You would never reach a moment where something stops you and says, "This is where the atom ends." And yet, atoms have a very specific, measurable size. Hydrogen is smaller than carbon. Carbon is smaller than cesium. These sizes are real. They determine how big molecules are, how large cells are, how much space your body takes up. So where does that size come from? What decides how big an atom is if there is no edge to define it? If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It means more than you might think. Now, let's begin. Let us start with something you already know, but have probably never thought deeply about. Everything around you is made of atoms. The chair you are sitting in, the air filling your lungs right now, the screen in front of you, your own body, every tissue, every cell, every molecule inside you. All of it, every last bit, is constructed from atoms. And every atom has a size. Hydrogen atoms are small. Carbon atoms are a bit larger. Cesium atoms are much larger still. These sizes are not random. They are specific, consistent, and measurable. Scientists have pinned them down with extraordinary precision. The size of a hydrogen atom is about 1/10 of a nanometer, roughly 1/10 billionth of a meter. That number is the same everywhere on Earth, everywhere in the solar system, everywhere across the observable universe. A hydrogen atom near a star in a distant galaxy is exactly the same size as a hydrogen atom in your fingertip. But here is the strange thing. If you could somehow zoom in on an atom, shrinking yourself down to a scale billions of times smaller than a grain of sand, you would not find a wall. You would not hit an edge. There is no surface, no shell, no hard boundary where the atom ends and empty space begins. An atom is not like a tiny marble. It is not like a billiard ball with a smooth, round exterior. It is not like any solid object you have ever encountered in your life. And yet it has a size, a definite, real, physical size that determines how large molecules are, how tightly atoms pack together when they form solids, how much space your body occupies, how much room everything in the universe takes up. So what gives an atom its size? What sets a boundary when there is no boundary? This is one of the deepest questions in all of physics, and the answer reaches into the strangest and most counterintuitive corners of how the universe actually works. To understand where atomic size comes from, we first need to understand what an atom actually is. And that story begins a very long time ago with nothing more than a thought experiment. About 2,400 years ago, a Greek philosopher named Democritus sat down and thought about matter. He asked a deceptively simple question. If you take a piece of gold and cut it in half, you get two smaller pieces of gold. Cut one of those in half again, and you get an even smaller piece. Keep cutting, keep dividing. Can you do this forever, splitting the gold into smaller and smaller fragments without end? Or is there a point where you reach something so small that it simply cannot be divided any further? Democritus argued that there must be a limit. At some point, you would reach a particle so tiny that no further cutting is possible. He called these particles atomos, from the Greek word meaning uncuttable. These were the fundamental building blocks of all matter. Everything in the world, he proposed, was made of these indivisible units arranged in different patterns. Different materials, gold, water, air, stone, were simply different arrangements of the same basic particles. It was a brilliant idea. It was remarkably close to the truth, and it was almost completely ignored for the next 2,000 years. Aristotle, who came after Democritus and whose enormous intellectual authority dominated Western thought for centuries, rejected atomism entirely. Aristotle believed matter was continuous and infinitely divisible. You could always cut smaller. There was no smallest piece. There was no flaw, no fundamental grain to the fabric of reality. And because Aristotle's influence was so immense, so deeply embedded in philosophy and education, and later in religious thinking, his view prevailed. Atoms remained a philosophical curiosity, an interesting speculation that most scholars dismissed as naive. It was not until the early 1800s that atoms made a serious comeback, and this time they returned through experiment rather than philosophy. A British chemist named John Dalton noticed something remarkable about chemical reactions. When elements combined to form compounds, they always combined in fixed ratios by mass. It did not matter how much hydrogen and oxygen you started with. When they reacted to form water, they always combined in the same proportions. 8 grams of oxygen for every 1 gram of hydrogen. Always, without exception. Carbon and oxygen combined in fixed ratios to form carbon dioxide. Nitrogen and hydrogen combined in fixed ratios to form ammonia. Every chemical reaction Dalton studied showed the same pattern. Fixed, predictable, unchanging ratios. Dalton realized this made perfect sense if matter was made of atoms with specific masses. If a water molecule always contains 2 hydrogen atoms and 1 oxygen atom, and if oxygen atoms are about 16 times heavier than hydrogen atoms, then you would always need 8 parts oxygen by mass for every 1 part hydrogen. The fixed ratios were not a coincidence. They were not an accident. They were a direct consequence of atoms being real, discrete units with definite individual masses. This was powerful evidence, but it was indirect. Nobody had seen an atom. Nobody had measured one directly. Nobody had touched one or isolated one. Atoms were still inferred from chemical patterns rather than observed in any concrete way. The question of what an atom actually looked like, what its internal structure might be, how big it was, what it was made of, remained completely open. Dalton imagined atoms as tiny solid spheres, like miniature billiard balls. That was the best anyone could do at the time. There was simply no way to probe something so small. The first real crack in the mystery came in 1897, when a British physicist named J.J. Thomson made a discovery that shook the very foundations of physics. Thomson was experimenting with cathode rays, streams of particles produced inside glass vacuum tubes when a high voltage is applied between 2 metal electrodes. These mysterious rays had been observed for decades, but nobody knew what they were made of. Thomson set out to find out. He applied electric and magnetic fields to the rays, measured how the particles deflected, and from those deflections, calculated the ratio of each particle's charge to its mass. What he found was astonishing. The particles in cathode rays were incredibly light. They were nearly 2,000 times lighter than the lightest known atom, hydrogen, and they carried a negative electric charge. Most importantly, these particles were identical, regardless of what material the cathode was made from. Whether the tube used aluminium or platinum or carbon, the particles were always the same. They were universal. Every type of atom seemed to contain them. Thomson had discovered the electron, and this discovery was revolutionary for one simple reason. If atoms contain electrons, then atoms are not indivisible. They have internal structure. They have parts. Democritus was wrong about atoms being uncuttable, but he was right that atoms exist as fundamental units of chemical elements. Atoms are just more complicated inside than anyone had imagined. Thomson proposed a model of the atom based on his discovery. He imagined the atom as a sphere of uniformly distributed positive charge, with electrons embedded throughout it, like raisins in a pudding. This became known as the plum pudding model. The positive charge was spread evenly throughout the full volume of the atom, and the negatively charged electrons sat within that positive medium, held in place by electrical attraction. The atom as a whole was electrically neutral because the total positive and negative charges balanced each other exactly. It was a reasonable guess based on the available evidence. It was also completely wrong. And what destroyed it was one of the most famous experiments in the entire history of science. In 1911, a New Zealand-born physicist named Ernest Rutherford, working at the University of Manchester in England, designed an experiment to probe the internal structure of the atom directly. Rutherford, along with his colleagues Hans Geiger and Ernest Marsden, fired alpha particles at an extremely thin sheet of gold foil. Alpha particles are helium nuclei, tiny but dense projectiles carrying positive charge and moving at tremendous speed, roughly 5% of the speed of light. They are much heavier than electrons, about 8,000 times more massive, giving them enough momentum to punch through thin material. If Thomson's plum pudding model was correct, with positive charge spread diffusely throughout the atom, the alpha particles should pass through the gold foil with only minor deflections. The diffuse positive charge would nudge them slightly off course, but nothing dramatic. It would be like rolling a bowling ball through a thin fog. The fog might slow it a tiny bit, but it would not stop it or turn it around. And indeed, most of the alpha particles sailed straight through the gold foil as if it were barely there. This was expected, but a small fraction did something utterly unexpected. Some deflected at large angles, veering sharply off their original paths, and a tiny number, roughly 1 in every 8,000, bounced almost straight backward, reversing direction entirely, as though they had slammed into something incredibly hard and dense. Rutherford was stunned. He later described his astonishment by saying, "It was as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you." This result made absolutely no sense under the plum pudding model. Diffuse positive charge spread throughout the atom could not possibly deflect a heavy, fast-moving alpha particle backward. The only explanation was that all of the positive charge and nearly all of the mass of the atom were not spread out evenly at all. They were concentrated in an incredibly tiny, incredibly dense region at the very center of the atom. This was the discovery of the atomic nucleus, and it completely transformed everything we thought we understood about the structure of matter. Rutherford's experiment revealed something that still astonishes people when they first grasp it. The atom is almost entirely empty space. The nucleus, which carries virtually all the atom's mass and all of its positive charge, occupies an almost unimaginably small fraction of the atom's volume. A typical atomic nucleus measures roughly 1 to 10 femtometers across. A femtometer is 1 quadrillionth of a meter, 1 millionth of a billionth of a meter. The full atom, the region that defines its measurable size, extends about 1/10 of a nanometer, roughly 100,000 times larger than the nucleus. Let that ratio sink in for a moment. If you scaled an atom up to the size of a large football stadium, the nucleus would be about the size of a small marble sitting right at the center of the field. Everything else, the stands, the field, the end zones, the walkways, the parking lots outside, all of that vast volume is where the electrons exist, and the overwhelming majority of it is simply empty. There is nothing there, no substance, no material, just space, with an occasional electron somewhere in it. This is not an approximation. This is not a metaphor stretched for dramatic effect. This is what atoms actually are. Enormous regions of nearly empty space centered on a tiny, dense core. The nucleus contains more than 99.9% of the atom's mass, packed into a volume roughly 1 million billion times smaller than the atom as a whole. The remaining space belongs to the electrons, particles so light that each one has roughly 1/1800th the mass of a single proton. Yet somehow these ghostly, lightweight particles define the entire size of the atom. Think about what this means for the world around you. The desk you might be resting your hand on right now feels solid. It resists your touch. It supports the weight of everything you place on it. But that desk is made of atoms that are overwhelmingly empty inside. If you could somehow remove all the empty space from every atom in a human body, compressing the remaining matter so that all the nuclei were packed together at nuclear density, everything that makes up a person would fit into a volume far smaller than a single grain of sand. All the mass of a human being, roughly 70 kilograms of bone and muscle and tissue and thought, compressed down to a speck you could barely see. The solidity you feel when you touch an object, the volume that objects occupy, the reason your hand does not pass through the table, none of that comes from the nucleus. It all comes from what the electrons are doing in that vast, empty space around it. The size of every object you have ever seen or touched is determined not by tiny, solid cores, but by electron behavior. Understanding that behavior is the key to understanding atomic size. So, after Rutherford's discovery, the picture of the atom looked roughly like this. A tiny, extraordinarily dense, positively charged nucleus sits at the center. Lightweight, negatively charged electrons exist somewhere in the vast space surrounding it. The positive nucleus attracts the negative electrons through the electromagnetic force, the same fundamental force that makes opposite charges attract, that makes magnets cling to your refrigerator, that holds molecules together and drives every chemical reaction in your body. This electromagnetic attraction is what binds the atom together. Without it, electrons would simply drift away into space and atoms would fall apart instantly. The obvious question was how the electrons were arranged around the nucleus. And the answer that seemed most natural, most intuitive, most satisfying was that electrons orbit the nucleus the way planets orbit a star. The gravitational pull of a star draws planets inward, but the planets are moving sideways fast enough that they continuously fall around the star rather than plunging into it. Their orbital speed balances the inward pull, creating stable, circular or elliptical paths that persist for billions of years without changing. By direct analogy, the electromagnetic pull of the nucleus draws electrons inward, but the electrons are moving fast enough that they orbit the nucleus rather than crashing into it. Their orbital motion balances the inward attraction, creating stable paths at fixed distances. This was the planetary model of the atom, and it was elegant, intuitive, and deeply satisfying. It connected the unimaginably small to the familiar large. It suggested that atoms were like miniature solar systems, with the nucleus playing the role of a star and the electrons playing the role of planets. There was just one devastating problem with this beautiful picture. The planetary model of the atom is catastrophically wrong. Not slightly wrong, not off in some minor technical detail. Fundamentally, irreparably, completely wrong, in a way that predicts the atom should not exist at all. And the reason it fails reveals something genuinely profound about the nature of physical reality at the smallest scales. The problem comes from classical electromagnetism, the theory developed by James Clerk Maxwell in the 1860s that describes how electric and magnetic fields behave and interact. Maxwell's equations are among the towering achievements in the history of human thought. They unified electricity and magnetism into a single, coherent framework. They predicted the existence of electromagnetic waves and showed that light itself is an electromagnetic wave. They have been tested and confirmed by countless experiments for more than 150 years. They work. They are reliable. and they make a very specific, unavoidable prediction about what happens when a charged particle moves along a curved path. When any charged particle accelerates, and moving in a circle absolutely counts as acceleration, because the direction of motion is constantly changing even if the speed stays the same, it must radiate electromagnetic energy. This is not optional. It is not a minor side effect that might or might not matter. It is a fundamental, inescapable consequence of Maxwell's equations. Any charged particle following a curved trajectory radiates energy, period. An electron orbiting a nucleus is a charged particle moving along a curved path. Therefore, according to Maxwell's equations, it must radiate energy. As it radiates, it loses energy. As it loses energy, its orbit decays and it spirals closer to the nucleus. As it spirals closer, it moves faster, curves more sharply, accelerates harder, and radiates energy even more intensely. The process feeds on itself in a vicious cycle, each moment of radiation leading to faster radiation the next moment. How long would this catastrophic spiral take? Not long at all. Calculations based on classical electromagnetism show that an electron orbiting a hydrogen nucleus would spiral inward and crash into the proton in roughly 16 trillionths of a second. Essentially instantaneous. Faster than any event you could ever perceive. Every atom in the universe should have collapsed almost the instant it formed. Matter should not exist. Chemistry should be impossible. Stars should never have ignited. You should not be here. Nothing should be here. And yet here you are, sitting somewhere, listening to these words, made of atoms that have been perfectly stable for billions of years. The hydrogen atoms in your body were forged in the first few minutes after the Big Bang, roughly 13.8 billion years ago, and they are exactly the same size today as they were then. They did not collapse. They did not spiral inward. They did not shrink even slightly over the entire history of the universe. Something is preventing the electrons from falling into the nucleus. Something holds them at a specific average distance, giving each type of atom a specific characteristic size. But classical physics, the physics of Newton's laws and Maxwell's equations, has absolutely no explanation for what that something is. This was the crisis that confronted physics at the dawn of the 20th century. The best theories available, theories that had been tested and confirmed by centuries of careful experiments, theories that could predict the motions of planets and the behavior of electromagnetic waves with breathtaking precision. These same theories said atoms are impossible. Electrons must radiate and spiral inward. Atoms must collapse. Matter cannot be stable. And the crisis was not limited to atoms. Classical physics was simultaneously failing to explain a growing list of phenomena at the smallest scales. It could not explain why heated objects glow the specific colors they do. It predicted that a hot object should emit infinite energy at short wavelengths, a result so absurd it was called the ultraviolet catastrophe. It could not explain why certain metals release electrons when light of a specific frequency shines on them, a phenomenon called the photoelectric effect. It could not explain the precise wavelengths of light emitted by hydrogen gas when heated, a pattern so regular and specific that it clearly followed some hidden rule that classical physics could not identify. Problem after problem mounted, each pointing to the same unsettling conclusion. At the scale of atoms and below, the familiar rules break down. The classical laws that describe the everyday world with such remarkable accuracy simply do not apply to the very small. The old physics was not exactly wrong, it was incomplete. It described a universe that works beautifully at human scales and above, but that fails entirely when you attempt to apply it to atomic and subatomic reality. Something fundamentally different was happening at those scales. something that demanded an entirely new way of thinking, an entirely new mathematical framework, an entirely new set of physical principles. That framework would eventually be called quantum mechanics, and it would not merely patch up the problems with the old physics, it would revolutionize our understanding of nature at the deepest level. It would explain why atoms are stable. It would explain where their sizes come from. It would reveal that electrons are nothing like tiny planets orbiting a central body, that the behavior of matter at the smallest scales is stranger, more alien, more counterintuitive, and ultimately more beautiful than anyone in the early 1900s could have anticipated. The old picture, the comfortable, reassuring picture of little electrons circling a nucleus on neat, predictable tracks like a miniature solar system, was about to be torn apart and replaced by something profoundly different. Something built on probability rather than certainty. Something involving invisible clouds of likelihood spread through space, fundamental limits on what can ever be known about a particle, and a deeply paradoxical principle in which confining something to a smaller region actually forces it to carry more energy. That paradox, that strange and deeply counterintuitive fact, turns out to be the single most important key to answering our original question. It is the reason atoms have the specific sizes they do. It is the reason matter occupies volume. It is, in a very real and concrete sense, the reason the physical universe exists in the form you experience every day. So classical physics said atoms are impossible. Electrons should radiate energy, spiral into the nucleus, and collapse in a trillionth of a second. But atoms do not collapse. They are stable. They have been stable for billions of years. Something was desperately wrong with the old picture, and what was needed was not a small repair, not a minor adjustment to existing equations, but an entirely new framework of physics. That framework arrived in the early 20th century, and it changed everything. The revolution started not with atoms directly, but with light. In the year 1900, a German physicist named Max Planck was trying to solve a stubborn problem about how hot objects radiate energy. Classical physics predicted that a heated object should radiate infinite energy at short wavelengths, which is obviously absurd. A glowing piece of iron does not vaporize you with infinite radiation the moment you heat it. Planck found a mathematical trick that fixed the problem. He proposed that energy is not emitted continuously in any amount you like, but rather in discrete packets, tiny, indivisible chunks he called quanta. Each quantum of energy was proportional to the frequency of the radiation. Higher frequency light carried more energy per quantum. Lower frequency light carried less. The proportionality constant linking energy to frequency became known as Planck's constant, one of the most fundamental numbers in all of physics. Planck himself was not entirely comfortable with this idea. He considered it a mathematical device, a calculating trick that happened to give the right answer. He did not necessarily believe energy really came in packets. But 5 years later, Albert Einstein took the idea seriously in a way Planck had not. Einstein used the concept of energy quanta to explain the photoelectric effect, the puzzling observation that certain metals release electrons when light of a specific minimum frequency shines on them, regardless of how bright that light is. Dim violet light ejects electrons from certain metals. Blindingly bright red light does not. Intensity does not matter. Only frequency matters. This makes no sense if light is a continuous wave. A brighter wave should deliver more energy, regardless of frequency, eventually knocking electrons free. But it makes perfect sense if light comes in individual packets, quanta, later called photons. Each photon carries a specific amount of energy determined by its frequency. A violet photon carries enough energy to knock an electron loose. A red photon, no matter how many you throw at the metal, does not carry enough energy per individual photon. You can hurl billions of red photons at the surface and none of them will eject an electron because each one individually lacks the required energy. It is like trying to break down a door by throwing tennis balls. You can throw millions of them and the door will not budge because no single tennis ball carries enough force. But one well-placed swing of a sledgehammer does the job. Einstein's explanation confirmed that light is not just a wave, it behaves as a stream of discrete particles, photons, each carrying a specific quantum of energy. This was deeply confusing because light also clearly behaves as a wave. It diffracts around obstacles, creating bending and spreading patterns. It interferes with itself, producing the bright and dark bands you see when light passes through narrow slits. These are exclusively wave behaviors. No stream of simple particles should produce interference patterns, yet light does both. It behaves like a wave in some experiments and like a stream of particles in others. This was wave-particle duality, and it was profoundly unsettling. How can something be both a wave and a particle? These seem like opposite concepts. A wave is spread out, extended through space, occupying a broad region simultaneously. A particle is localized, concentrated in a tiny point, existing in one specific place at one specific time. Light appeared to be both at once, depending on how you looked at it. And then, in 1924, a French physicist named Louis de Broglie proposed something even more radical. If light, which everyone had assumed was purely a wave, also behaves like a particle, then maybe matter, which everyone assumed was purely particulate, also behaves like a wave. Maybe electrons, protons, atoms, and even larger objects have wave properties. Maybe wave-particle duality is not unique to light. Maybe it is a universal feature of everything in nature. De Broglie proposed that every particle has an associated wavelength determined by its momentum. The faster and heavier a particle is, the shorter its wavelength. For large, everyday objects, a thrown baseball, a rolling bowling ball, a walking person, the wavelength is so fantastically tiny, so many orders of magnitude smaller than anything measurable, that wave behavior is completely undetectable. The wave nature of a baseball is real in principle, but utterly invisible in practice. It plays no role whatsoever in how baseballs move. But for tiny, lightweight particles like electrons, the wavelength is significant. An electron moving at typical atomic speeds has a wavelength roughly comparable to the size of an atom itself, about 1/10 of a nanometer. At this scale, the wave nature of the electron is not a minor correction to its behavior. It dominates. It is the single most important thing about the electron. Everything the electron does at atomic scales is controlled by its wave properties. This was confirmed experimentally just a few years later. In 1927, two independent experiments, one by Clinton Davison and Lester Germer in the United States, another by George Paget Thompson in England, showed that beams of electrons fired at crystal surfaces produce diffraction patterns. The electrons spread out, interfere with each other, and create patterns of bright and dark bands on a detector, exactly the way light waves do when they pass through a narrow opening. Electrons are waves, not metaphorically, not approximately, literally. They diffract and interfere just like water waves or sound waves or light waves. The wave nature of the electron is an experimental fact, confirmed by countless experiments over nearly a century. But even these early experiments could not prepare people for what came next. In the decades that followed, physicists refined the experiment to its most disturbing form. Instead of firing a beam of many electrons at a barrier with two narrow slits, they fired electrons one at a time. A single electron was released from a source, traveled through space, and hit a detector screen on the other side of the two slits. Each individual electron arrived at the screen as a single dot, a tiny impact at one specific point, behaving exactly like a particle. There was nothing wave-like about any single detection, just a dot, then another dot, then another. But as the dots accumulated, hundreds, thousands, tens of thousands of individual electrons arriving one at a time, something astonishing emerged. The dots did not scatter randomly. They did not cluster in two bands directly behind the two slits, which is what you would expect if each electron simply passed through one slit or the other like a tiny bullet. Instead, the dots gradually built up an interference pattern, alternating bands of many dots and almost no dots, bright fringes and dark fringes. Exactly the pattern a wave would produce when passing through two openings and interfering with itself. Each electron was fired alone. There was nothing else in the apparatus to interfere with. No other electron was present during the journey. And yet, the pattern that emerged was unmistakably the pattern of a wave that had passed through both slits simultaneously and interfered with itself on the other side. A single electron, traveling alone, somehow behaved as though it went through both slits at the same time. This is perhaps the single most important experiment in the history of physics. It demonstrates that an electron is not simply a particle that happens to have wave properties. It is something fundamentally different from anything in everyday experience. When it travels through space, it does not follow a single definite path. It does not go through one slit or the other. It exists in a state that encompasses both possibilities at once, spreading through space like a wave, only to appear as a localized dot when it finally interacts with the detector. The act of detection forces it into a specific location, but before that moment, it has no specific location. It is everywhere its wave nature allows it to be. This experiment shattered the last vestiges of the classical picture. Electrons are not tiny balls following clean trajectories. They are quantum objects that obey rules unlike anything in the macroscopic world. And understanding those rules is the key to understanding why atoms have the sizes they do. So what does it mean for an electron to be a wave? This is where things get genuinely strange, and where we start to see why atoms have the sizes they do. In classical physics, an electron was imagined as a tiny particle, a little dot of matter with a definite position and a definite velocity at every instant. You could, in principle, point to the electron and say it is right here, moving in that direction at that speed. Its trajectory was a clean, predictable line through space, fully determined by its starting conditions and the forces acting on it. Quantum mechanics says this picture is wrong. An electron does not have a definite position until it is measured. Between measurements, it does not exist at one specific point. Instead, its existence is described by something called a wave function, a mathematical object that assigns a number to every point in space at every moment in time. The wave function is usually represented by the Greek letter that physicists pronounce psi. It is not a physical wave you can see or touch. It is an abstract mathematical entity. But it encodes everything that can possibly be known about the electron. The wave function itself does not directly tell you where the electron is. What it tells you is something more subtle and more profound. If you take the wave function at any given point in space and calculate its magnitude squared, you get the probability of finding the electron at that point if you were to look for it. The wave function is a probability map. It tells you not where the electron is, but where the electron is likely to be found. Regions where the wave function is large have a high probability of containing the electron. Regions where the wave function is small have a low probability. Regions where the wave function is zero have no chance at all. This is not a statement about our ignorance. It is not that the electron is really somewhere specific and we just do not know where. Quantum mechanics says there is no specific location. The electron genuinely does not have a definite position. It exists as a spread-out cloud of probability, a fuzzy distribution of likelihood smeared across a region of space. When you measure its position, the wave function collapses to a specific point and the electron appears there. But before that measurement, asking where the electron is has no answer. Not because we lack information, but because the question itself does not apply. The electron is not anywhere in particular. It is everywhere. Its wave function is non-zero, all at once, with varying degrees of probability. This is the electron cloud you may have heard about. When people talk about the cloud of electrons surrounding an atomic nucleus, they are talking about this probability distribution. The cloud is densest where the wave function's magnitude is largest, where you are most likely to find the electron. It fades gradually toward the edges, getting thinner and thinner, but never quite reaching zero. There is no sharp cutoff, no boundary, no wall. The probability of finding the electron decreases smoothly as you move away from the nucleus, trailing off into nothingness without ever reaching a clean edge. And this is why an atom has no hard surface. The electron cloud does not end. It fades. There is no point where you can draw a line and say the atom stops here. In principle, there is a tiny but non-zero probability of finding the electron extraordinarily far from the nucleus, meters away, light years away even. The probability is so vanishingly small that it is completely negligible, indistinguishable from zero for any practical purpose. But mathematically, it is not exactly zero. The atom does not have a boundary. It has a region of high probability surrounded by rapidly diminishing tails. So when scientists talk about the size of an atom, they are not describing a hard edge. They are describing the region where the electron is most likely to be found. The size of an atom is the size of its electron cloud, the spatial extent of the probability distribution for its outermost electrons. This is a real, measurable, well-defined quantity, but it is fundamentally a quantum mechanical quantity. It is the extent of a probability cloud, not the diameter of a solid sphere. Now comes the crucial question. What determines how wide that cloud is? What sets the size of the probability distribution? Why is a hydrogen atom about 1/10 of a nanometer across and not 100 times bigger or 1,000 times smaller? The answer lies in a principle that is arguably the most important idea in all of quantum mechanics. In 1927, a German physicist named Werner Heisenberg discovered something about the nature of measurement at quantum scales that sent shock waves through the entire physics community. He showed that there are fundamental, absolute, unbreakable limits on how precisely you can simultaneously know certain pairs of properties of a quantum particle. The most famous pair is position and momentum. Momentum is essentially mass times velocity, a measure of how fast something is moving and in what direction. Heisenberg's uncertainty principle states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a limitation of your instruments. It is not that your measuring device disturbs the particle and introduces error. The uncertainty is intrinsic. It is built into the fabric of reality. The particle simply does not have both a precise position and a precise momentum at the same time. These properties are fundamentally blurred. Nature itself is uncertain at this level. Mathematically, the uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to a specific minimum value related to Planck's constant. You cannot beat this limit. No instrument, no matter how advanced, no technology, no matter how sophisticated, can ever measure both position and momentum of a quantum particle with unlimited precision simultaneously. The universe does not allow it. Now here is where this connects to atoms in the most powerful way. Think about what happens when you try to confine an electron to a smaller and smaller region of space. Confining the electron means reducing the uncertainty in its position. You are squeezing it into a tighter volume, forcing it to be in a more specific location. But Heisenberg's principle says that reducing the uncertainty in position forces the uncertainty in momentum to increase. And increased uncertainty in momentum means the electron can have higher and higher momenta. Higher momentum means higher kinetic energy, the energy of motion. This is not optional, it is automatic and unavoidable. Confine an electron into a smaller box and its kinetic energy goes up. Squeeze it tighter and its kinetic energy goes up more. Try to cram it into an infinitely small space, into a single point like the nucleus, and its kinetic energy shoots toward infinity. The tighter you confine a quantum particle, the more violently it resists that confinement by possessing ever greater energy. Think of it this way. Imagine trying to hold a vibrating, buzzing particle in your hands. If you cup your hands loosely, giving it lots of room, it bounces around gently inside the space you have provided. Now bring your hands closer together, compressing the space. The particle bounces more violently, ricocheting faster and harder off the walls of its shrinking prison. Squeeze your hands tighter still, and the particle becomes ferocious, hammering against your palms with tremendous force. The smaller the space, the more violent the resistance. You can never fully close your hands because the energy required to compress the particle to zero size would be infinite. This is an imperfect analogy, but it captures the essential physics. Confining a quantum particle costs energy. The cost increases as the confinement gets tighter. This is sometimes called quantum confinement energy or zero-point energy, and it is a direct and inescapable consequence of the uncertainty principle. It has no classical analogue. Nothing in the everyday physics of Newton and Maxwell predicts anything like it. It is purely quantum mechanical, arising entirely from the wave nature of matter and the fundamental limits on simultaneous knowledge of position and momentum. Now apply this to an electron in an atom. The electron feels two competing influences. On one side, there is the electromagnetic attraction between the negatively charged electron and the positively charged nucleus. This attraction pulls the electron inward toward the nucleus. The closer the electron gets to the nucleus, the lower its electromagnetic potential energy becomes. From a purely electromagnetic standpoint, the electron would gain energy by falling all the way into the nucleus, just as a ball gains kinetic energy by rolling to the bottom of a hill. The lowest possible electromagnetic energy corresponds to the electron sitting right on top of the nucleus at zero distance. But on the other side, there is the quantum confinement cost. If the electron falls closer to the nucleus, it occupies a smaller region of space. Its position becomes better defined. And according to Heisenberg's principle, its momentum uncertainty, and thus its kinetic energy, must increase. The closer the electron gets to the nucleus, the more kinetic energy it gains from quantum confinement. These two effects oppose each other. Electromagnetic attraction lowers the energy as the electron moves inward. Quantum confinement raises the energy as the electron is squeezed into a smaller volume. The total energy of the electron is the sum of both contributions. The negative electromagnetic potential energy pulling it inward, and the positive kinetic energy from quantum confinement pushing outward. There is an optimum distance, a sweet spot, a point where the total energy is minimized. To see why this balance point exists, and why it sits where it does, imagine experimenting with the electron cloud's size. Start with the actual equilibrium size of a hydrogen atom, about 1/10 of a nanometer, and imagine artificially shrinking the cloud to half that radius. What happens to the two energy contributions? The electromagnetic potential energy roughly doubles in strength because the electron is now twice as close to the proton. That is again a reduction in potential energy. But the confinement cost does not merely double, it quadruples. When you halve the radius, you are confining the electron to a volume 8 times smaller, and the kinetic energy scales as the inverse square of the confinement size. The kinetic energy penalty grows much faster than the electromagnetic reward. The total energy goes up. The atom is less stable at this smaller size. Now imagine expanding the cloud to twice its equilibrium radius. The confinement cost drops to 1/4 of its original value. That is a significant savings. But the electromagnetic attraction also weakens because the electron is now twice as far from the proton on average. The potential energy becomes half as negative. The electromagnetic penalty of being farther away outweighs the quantum savings of being less confined. The total energy goes up again. The atom is also less stable at this larger size. Only at the equilibrium radius, the actual size of the hydrogen atom, do the two contributions balance in a way that produces the lowest possible total energy. Shrink below it, and the confinement cost overwhelms you. Expand beyond it, and the electromagnetic loss overwhelms you. The ground state sits in a valley between two rising slopes, and the atom naturally settles at the very bottom. This is not an arbitrary resting place. It is mathematically unique. Given the values of the fundamental constants, there is exactly one distance at which the total energy reaches its minimum. That distance is the size of the atom. The lowest total energy, the ground state, sets a specific characteristic distance from the nucleus. For hydrogen, the simplest atom with one proton and one electron, this distance works out to about 5.3 hundredths of a nanometer. This value is called the Bohr radius, named after the Danish physicist Niels Bohr, who first calculated it in 1913 using an early and somewhat simplified version of quantum theory. Modern quantum mechanics, developed by Erwin Schrödinger, Werner Heisenberg, and others in the mid-1920s, gives the same answer, but with a far deeper and more rigorous justification. The Bohr radius is not the maximum extent of the electron cloud. The cloud extends well beyond this distance, fading gradually. But the Bohr radius represents the most probable distance from the nucleus. It is where the probability of finding the electron is highest. It defines the characteristic scale of the hydrogen atom. When scientists say a hydrogen atom is about 1/10 of a nanometer across, they are describing the region where the electron cloud is concentrated, and the Bohr radius is the number at the heart of that size. This is extraordinary. The size of the simplest atom in the universe is not set by any mechanical structure, not by a wall, not by a shell, not by some physical barrier at the boundary. It is set by a balance between two fundamental aspects of nature: the electromagnetic force, which governs the attraction between charges, and the uncertainty principle, which governs the quantum behavior of matter at small scales. These two effects compete with each other inside every atom, and the size of the atom is the distance at which their competition reaches equilibrium. You can calculate the Bohr radius from first principles, using nothing but a handful of fundamental constants. Planck's constant, which sets the scale of quantum effects; the mass of the electron, which determines how much kinetic energy confinement produces; the charge of the electron, which determines the strength of the electromagnetic attraction; and the speed of light, which enters through the fine structure constant, a dimensionless number that measures the overall strength of electromagnetic interactions. Combine these constants in the right way, and you get the Bohr radius, 5.3 hundredths of a nanometer. That is it. No adjustable parameters, no free choices. The size of a hydrogen atom is completely determined by the fundamental constants of nature. This means the size of a hydrogen atom is the same everywhere in the universe, and has been the same since the first hydrogen atoms formed in the minutes after the Big Bang. A hydrogen atom 13 billion light-years away is exactly the same size as one in your body right now. A hydrogen atom that formed in the first few 100,000 years of the universe's existence is exactly the same size as one that formed yesterday in the upper atmosphere. The constants of nature do not change, so the balance between electromagnetic attraction and quantum confinement does not change, so the size of the atom does not change. This also explains why atoms are stable. The electron in a hydrogen atom does not spiral into the nucleus because it cannot. The ground state is the lowest possible energy level. There is nowhere lower to go. The electron is already in the configuration that minimizes total energy. If you tried to push it closer to the nucleus, you would have to supply energy to overcome the confinement cost. The ground state is like the bottom of a valley. A ball at the bottom of a valley does not roll further downhill because there is no further downhill to roll to. Similarly, an electron in the ground state does not fall closer to the nucleus because doing so would increase, not decrease, its total energy. This is the quantum mechanical resolution of the catastrophe that classical physics predicted. Classical physics said the electron should radiate energy and collapse into the nucleus in a trillionth of a second. Quantum mechanics says there is a minimum energy state, a ground state, and once the electron reaches it, it stays there indefinitely. It does not radiate. It does not lose energy. It does not spiral inward. The atom is stable, permanently, because quantum mechanics provides a floor that the electron cannot fall below. And the distance at which this floor is set, the spatial extent of the ground state wave function, is what we call the size of the atom. The atom's size is not a boundary. It is an equilibrium. It is the place where the electromagnetic pull inward and the quantum pressure outward reach a perfect, exquisite balance. Move the electron inward from this point, and the quantum cost rises faster than the electromagnetic benefit. Move it outward, and the electromagnetic penalty grows faster than the quantum savings. The ground state is the unique distance where total energy is at its absolute minimum. So the answer to our central question begins to take shape. An atom gets its size from the quantum behavior of electrons. The electromagnetic force tries to pull electrons all the way into the nucleus. Quantum mechanics refuses to allow it. The uncertainty principle imposes a cost on confinement, a cost that rises sharply as the electron is squeezed into smaller and smaller volumes. The balance between these two effects produces a stable electron cloud with a characteristic spatial extent. That extent is the size of the atom. Without quantum mechanics, atoms would have no size at all. Electrons would collapse into the nucleus. There would be no electron cloud, no spatial extent, no volume. Matter would compress to nuclear density. Every atom in your body would shrink to a speck far smaller than a grain of sand. The physical world as you experience it, objects with volume, surfaces you can touch, a body you can move through space, none of it would exist. Quantum mechanics is not some exotic abstraction relevant only in laboratories with billion-dollar equipment. It is the reason you have a size. It is the reason anything has a size. It is operating right now inside every atom in your body, in the walls around you, in the ground beneath you, in the air you breathe. The quantum balance between electromagnetic attraction and confinement energy is holding open every atom in the universe at this very moment, giving matter its volume, giving objects their shape, giving you the physical world you live in. But hydrogen is just the beginning. It is the simplest atom, with one proton and one electron. The universe contains 92 naturally occurring elements, from hydrogen all the way up to uranium, each with a different number of protons and a different number of electrons. And every single one of those elements has a different atomic size. Helium is smaller than hydrogen. Lithium is larger. Sizes rise and fall across the periodic table in patterns that are not random, not arbitrary, but deeply connected to how electrons fill energy levels around nuclei of increasing charge. Understanding those patterns requires going beyond the simple two-body tug-of-war of hydrogen and into the richer, more complex quantum mechanics of many electron atoms. Hydrogen gave us the essential insight. The size of an atom is set by a quantum balance between electromagnetic attraction pulling the electron inward and confinement energy pushing outward. But hydrogen is the simplest atom in existence. One proton, one electron, nothing else. The real universe is not made of hydrogen alone. It contains 92 naturally occurring elements, from the lightest, hydrogen, to the heaviest found in nature, uranium. Every one of these elements has a different number of protons in its nucleus and a different number of electrons surrounding it, and every one of them has a different atomic size. Some atoms are tiny, some are remarkably large. These sizes follow patterns that are specific, repeatable, and deeply connected to the quantum rules governing how electrons arrange themselves around nuclei of increasing charge. To understand why each element has its own unique size, we need to go beyond the simple picture of one electron balanced against one proton. We need to understand how electrons fill the space around a nucleus when there are many of them, and that requires understanding something called energy levels. In the hydrogen atom, the electron does not just have one possible state, it has many. The ground state, the lowest energy configuration we discussed, is only the first. Above it sits a ladder of higher energy states, each corresponding to a larger, more spread out electron cloud. The electron can occupy any of these states, but only these states. It cannot exist at an energy between two rungs of the ladder. The allowed energies are quantized, meaning they come in specific, discrete values with gaps between them where no electron state exists. This quantization is not something imposed from outside. It arises naturally from the mathematics of the Schrödinger equation, the master equation of quantum mechanics that describes how wave functions behave. When you solve this equation for an electron bound to a nucleus, you do not get a continuous range of solutions. You get a discrete set. Each solution corresponds to a specific energy level and a specific spatial pattern for the electron cloud. These patterns are called orbitals. An orbital is not an orbit. The word sounds similar, but the meaning is fundamentally different. An orbit is a definite path through space, a track that a planet or satellite follows around a central body. An orbital is a three-dimensional probability cloud describing where an electron is likely to be found. It has a shape, a size, and an orientation in space, but it does not trace a line. It fills a region. The electron does not travel along a path within the orbital. It exists as a smeared-out presence throughout the entire volume of the orbital simultaneously, with varying probability at different points. Each energy level in an atom is characterized by a principal quantum number, traditionally labeled with the letter n. The lowest energy level has n equal to 1. The next has n equal to 2, then 3, 4, 5, and so on. As n increases, two things happen. The energy of the electron increases, meaning it is less tightly bound to the nucleus, and the average distance of the electron from the nucleus increases, meaning the orbital is physically larger. Higher energy levels correspond to bigger electron clouds. An electron in the n equals 1 level hugs close to the nucleus. An electron in the n equals 5 level extends far out into space, occupying a much larger volume. But the principal quantum number is not the whole story. Within each energy level, there are sublevels with different orbital shapes. These shapes are labeled with letters that come from an old spectroscopic tradition: S, P, D, and F. Each letter describes a distinct three-dimensional geometry for the electron cloud. An s orbital is spherical. It looks like a fuzzy ball centered on the nucleus, densest at the center and fading smoothly outward in all directions equally. Every energy level has one s orbital. The 1s orbital, the ground state of hydrogen, is the smallest and most compact. The 2s orbital is larger. The 3s is larger still. Each successive s orbital is a bigger sphere with more internal structure, more nodes, regions where the probability drops to zero before rising again farther out. A p orbital is different. It has two lobes extending in opposite directions from the nucleus, like a dumbbell or a figure 8 stretched out along one axis. There is a node at the nucleus itself, a plane where the probability of finding the electron is exactly zero.
P orbitals come in sets of 3, each oriented along a different axis in space. One along the x direction, one along the y direction, one along the z direction. They first appear at the n equals 2 level. There are no p orbitals in the first energy level. This matters enormously for atomic structure, as we will see. D orbitals are more complex still, with 4 lobes arranged in a cloverleaf pattern, or, in one special case, a dumbbell with a donut around its middle. They come in sets of 5 with different orientations, and first appear at n equals 3. F orbitals are even more elaborate, with 8 lobes in intricate arrangements. They come in sets of 7 and first appear at n equals 4. Each orbital can hold a limited number of electrons. This limit comes from a fundamental principle discovered by the Austrian physicist Wolfgang Pauli in 1925. The Pauli exclusion principle states that no 2 electrons in an atom can occupy exactly the same quantum state. Every electron must differ from every other electron in at least one quantum property. Since each orbital is defined by a specific set of quantum numbers, and since each electron also has a property called spin that can take one of exactly 2 values, each individual orbital can hold at most 2 electrons, one with spin up and one with spin down. No more. 2 electrons per orbital is an absolute, unbreakable limit. This changes everything about how atoms are built. If electrons could all crowd into the lowest orbital, every atom would have all its electrons packed into a tiny 1-second cloud hugging the nucleus. Every atom would be roughly the same small size. Chemistry as we know it would not exist. Molecules would not form the way they do. The periodic table would be meaningless. The diversity of matter, the richness of chemical behavior, the entire material complexity of the universe would vanish. But the exclusion principle forbids this. Only 2 electrons can fit into the 1-sex orbital. A third electron is locked out. It must go to the next available orbital, which is higher in energy and larger in size. A 4th electron fills that orbital's remaining slot. A 5th must move to yet another orbital. And so the electrons stack upward through the energy levels, filling orbitals from the bottom up, each new electron forced into a progressively higher, more expansive state. This filling process follows a specific order. The 1-sex orbital fills first because it has the lowest energy, then the 2-sex orbital, then the 3 2p orbitals, then the 3-sets orbital, then the 3 3p orbitals, then the 4-sets orbital, which actually has slightly lower energy than the 3d orbitals due to a subtle quantum effect related to how close its electron cloud gets to the nucleus. Then the 5 3d orbitals fill. This pattern, sometimes called the Aufbau principle from the German word for building up, determines the electron configuration of every element in the periodic table. Consider a few examples. Hydrogen has 1 proton and 1 electron. That electron goes into the 1-sex orbital, the smallest and lowest energy state. The atom is small. Helium has 2 protons and 2 electrons. Both electrons fit into the 1-sex orbital, one with spin up and one with spin down. The 1-sex orbital is now completely full, but helium's nucleus has 2 protons instead of hydrogen's 1,
which means twice the positive charge pulling the electrons inward. This stronger electromagnetic attraction squeezes the electron cloud tighter. Despite having one more electron than hydrogen, helium is actually smaller, significantly smaller. The stronger nuclear pull wins. Lithium has 3 protons and 3 electrons. 2 electrons fill the 1s orbital. The third electron is excluded. It must occupy the 2s orbital, the next available state. The 2s orbital is in the second energy level, much larger than the first.
So even though lithium has 3 protons pulling inward, that third electron sits in a cloud that extends much farther from the nucleus. Lithium is substantially larger than either hydrogen or helium. The jump to a new energy level creates a dramatic increase in size. This is the first glimpse of a pattern that repeats across the entire periodic table. Every time the outermost electrons are forced into a new, higher energy level, the atom gets significantly bigger. The size of an atom is determined primarily by which energy level its outermost electrons occupy. Inner electrons sit in compact clouds close to the nucleus. Outer electrons define the atom's effective boundary. It is the outermost electron cloud that another atom encounters when 2 atoms approach each other. It is the outermost electrons that participate in chemical bonding. And it is the outermost energy level that sets the atom's size. Now let us follow what happens as we move across a row of the periodic table. Start with lithium, which begins the second row. Lithium has 3 protons and 3 electrons. 2 electrons fill the inner 1s orbital. 1 electron occupies the outer 2s orbital. The atom is large because that outer electron is in a high, extended energy level. Move 1 step to the right to beryllium. 4 protons, 4 electrons. 2 electrons in the 1s orbital, 2 in the 2s orbital. The nucleus now has 4 protons instead of 3. The stronger positive charge pulls all the electrons, including the outer ones, slightly closer. Beryllium is a bit smaller than lithium. Continue to boron. 5 protons, 5 electrons. The 5th electron enters a 2p orbital. The nuclear charge has increased again. The pull on the outer electrons is stronger still. Boron is slightly smaller than beryllium. Then carbon, nitrogen, oxygen, fluorine, each adding 1 more proton and 1 more electron. The new electron enters an orbital in the same energy level, the second level. But the nuclear charge increases by 1 with each step. Each additional proton strengthens the electromagnetic pull on every electron in the atom, drawing the entire cloud inward slightly. You might expect that adding an electron would make the atom bigger. After all, there is more stuff now, more negative charge surrounding the nucleus. But the new electron enters the same energy level as the previous outer electrons. It does not extend the cloud outward into a new, larger shell. Meanwhile, the extra proton in the nucleus does pull everything inward. The net effect is that the atom shrinks. Atoms generally get smaller as you move from left to right across a row of the periodic table. More protons in the nucleus, pulling on electrons in the same energy level, produce a tighter, more compact electron cloud. By the time you reach neon, at the end of the second row, you have 10 protons and 10 electrons. The first and second energy levels are completely full. Neon is substantially smaller than lithium, even though it has more than 3 times as many electrons. The powerful 10-proton nucleus has pulled the entire electron cloud inward, compressing it despite the presence of additional electrons. Then something dramatic happens. The next element, sodium, has 11 protons and 11 electrons. The first 2 energy levels are completely filled with 10 electrons. The 11th electron has nowhere to go in those levels. It must enter the 3s orbital, the first orbital of the third energy level. This is a much larger orbital than anything in the second level. sodium is dramatically bigger than neon. The jump to a new principal energy level causes a sudden, sharp increase in atomic size. The same pattern that made lithium so much bigger than helium now makes sodium so much bigger than neon. And then the shrinking begins again. As we move across the third row, from sodium to magnesium to aluminium to silicon to phosphorus to sulfur to chlorine to argon, each step adds one proton and one electron. The electrons enter orbitals in the third level, not extending to a new level. The nuclear charge increases step by step, pulling the cloud tighter. Atoms shrink across the row. Argon, at the end, is much smaller than sodium at the beginning. This produces the characteristic zigzag pattern of atomic sizes across the periodic table. Sizes plummet across each row as increasing nuclear charge compresses the electron cloud. Then sizes spike upward at the start of the next row as the outermost electron is forced into a new, higher energy level. Plummet, spike. Plummet, spike. Row after row, the same pattern repeats. But there is a second trend, equally important. As you move down a column of the periodic table, atoms get larger. Lithium, sodium, potassium, rubidium, cesium, francium. Each of these elements sits at the start of its respective row, each with one electron in the outermost energy level. Lithium's outer electron is in the second level, sodium's is in the third, potassium's is in the fourth, rubidium's is in the fifth, cesium's is in the sixth. Each step down the column places the outer electron in a higher principal energy level, a larger orbital, farther from the nucleus. Now it is true that going down the column also adds more protons to the nucleus. Cesium has 55 protons, enormously more than lithium's 3. Should not that much stronger nuclear charge pull the electrons in tightly, making cesium very small? It would, except for one crucial factor: shielding. Shielding is one of the most important concepts in understanding atomic size. The idea is straightforward. In a many-electron atom, the inner electrons sit between the nucleus and the outer electrons. These inner electrons carry negative charge. From the perspective of an outer electron looking inward, it does not see the full positive charge of the nucleus. It sees the nuclear charge partially cancelled, partially screened, partially blocked by the negative charge of all the inner electrons crowded closer to the nucleus. Consider cesium. Its nucleus contains 55 protons, a powerful positive charge. But between the nucleus and the outermost electron sit 54 other electrons, arranged in completely filled inner energy levels. Those 54 inner electrons carry 54 units of negative charge, almost perfectly cancelling the 55 units of positive charge in the nucleus. The outermost electron, sitting far out in the 6th energy level, feels an effective nuclear charge of roughly 1. Not 55, roughly 1. Almost all of the nuclear charge is screened away by the fortress of inner electrons. This is why cesium is enormous. Its outermost electron is in a very high energy level, which means a very large orbital. And that electron feels almost no net pull from the nucleus because the inner electrons absorb nearly all of it. The confinement pressure from quantum mechanics easily balances the feeble residual electromagnetic attraction. The electron cloud spreads out to a large radius. Cesium is one of the biggest atoms in the entire periodic table, with an atomic radius of about 260 picometers. That is nearly 5 times larger than a hydrogen atom. Contrast this with helium, one of the smallest atoms. Helium has 2 protons and 2 electrons, both in the 1s orbital, the lowest and most compact energy level. There are no inner electrons providing shielding. Both electrons feel nearly the full 2-proton nuclear charge. The electromagnetic pull is strong relative to the quantum confinement cost at this level.
the electron cloud is squeezed tight. Helium's atomic radius is only about 31 picometers, making it almost 9 times smaller than cesium. The difference between cesium and helium is not a minor variation.
It is a factor of roughly 8 to 9 in radius. In volume, which scales as the cube of the radius, the difference is a factor of several hundred. Cesium atoms take up hundreds of times more space than helium atoms, and this enormous variation in size arises entirely from quantum mechanics. From how many electrons each atom has, which energy levels those electrons fill, how strongly the nucleus pulls them inward, and how effectively inner electrons shield outer electrons from that pull. Let me describe one more subtlety that matters for atomic size, because it helps explain some of the finer details in the periodic trends. Not all electrons in the same principal energy level are equally effective at shielding, and not all orbitals in the same level have the same average distance from the nucleus. An electron in an s orbital, even a high-level s orbital, has a wave function that penetrates close to the nucleus. The probability cloud of an s orbital has its highest density near the nucleus, then falls off, then may rise again at larger distances due to the radial structure of the wave function. This penetration means an s electron feels the nuclear charge more strongly than a p electron in the same energy level, because the p electron's probability is concentrated farther out and has a node right at the nucleus where the probability is 0. Similarly, a p electron penetrates closer than a d electron, and a d electron penetrates closer than an f electron. This ordering means that within a given energy level, s electrons are held more tightly than p electrons more tightly than d electrons, and d electrons more tightly than f electrons. It also means s electrons are more effective at shielding outer electrons because they spend more time close to the nucleus, between the nucleus and anything farther out. This penetration effect is why the filling order of orbitals does not simply go 1s, 2s, 2p, 3s, 3p, 3d in strict order of principal quantum number. The 4s orbital actually fills before the 3d orbitals because 4s electrons penetrate so close to the nucleus that their effective energy is lower than that of 3d electrons. The filling order is a consequence of these penetration effects, combined with electron-electron interactions, and it determines the structure of the periodic table itself. This is where the periodic table's shape comes from. The table is not a random arrangement of elements, it is a map of electron filling. Each row corresponds to the filling of a new principal energy level for the outermost electrons. The short rows at the top, hydrogen and helium in the first, lithium through neon in the second, correspond to filling s and p orbitals. The longer rows in the middle include d orbitals as they begin to fill, creating the transition metals. The even longer rows at the bottom, with the lanthanides and actinides pulled out below the main table, include f orbitals. Every detail of the periodic table's structure, its rows, its columns, its blocks, its shape, reflects the quantum mechanical rules governing electron orbitals. And every trend in atomic size across that table, the shrinking across rows, the growing down columns, the occasional exceptions and subtle variations, traces back to the interplay of nuclear charge, energy levels, shielding, and orbital penetration. The Russian chemist Dmitry Mendeleev organized the first widely recognized periodic table in 1869, decades before anyone understood quantum mechanics or even knew that electrons existed. He arranged elements by atomic mass and noticed that chemical properties repeated at regular intervals. Elements in the same column behaved similarly. Mendeleev did not know why. He had discovered an empirical pattern without understanding its cause. The cause,
the deep explanation for why the periodic table exists and why it has the structure it does, is quantum mechanics.
Every regularity Mendeleev observed, every repeating chemical property, every family of elements that share similar behavior, all of it arises from the quantum rules governing how electrons fill orbitals around nuclei. There is also a rule governing how electrons distribute themselves among orbitals of equal energy. When electrons begin filling a set of p orbitals, for example, they do not both pile into the same p orbital first. Instead, they spread out. Each of the three p orbitals gets one electron before any of them gets a second. This is known as Hund's rule, named after the German physicist Friedrich Hund. The reason is that electrons repel each other because they all carry negative charge. By occupying separate orbitals, the electrons stay farther apart on average, reducing their mutual repulsion and lowering the total energy. Hund's rule, combined with the exclusion principle and the Aufbau filling order, completely determines the electron configuration of every element in the periodic table. And from the electron configuration, you can predict the atom's size, its chemical properties, its bonding behavior, its reactivity, its magnetism, and much more. All of it flows from quantum mechanics. All of it traces back to wave functions, energy quantization, and the fundamental constants of nature. Let me bring this together by walking down one column of the periodic table, the column known as the alkali metals. These are the elements with one electron in their outermost energy level. Lithium is first, with its outer electron in the second level. Sodium below it has its outer electron in the third level. Potassium is next, outer electron in the fourth level. Then rubidium in the fifth. Then cesium in the sixth. Then francium in the seventh, though francium is so radioactive and rare that its properties are difficult to measure precisely. Each step down this column adds a complete new inner shell of electrons and places the outermost electron in a higher energy level farther from the nucleus. The nuclear charge increases substantially with each step. Cesium has 55 protons compared to lithium's 3. But the shielding provided by the 54 inner electrons almost completely neutralizes that charge. The outermost electron in cesium barely feels the nucleus. It sits in an enormous, diffuse, sixth-level orbital, weakly bound, easy to pull away. This is why cesium is so chemically reactive. Its outer electron is loosely held, ready to be lost in chemical reactions at the slightest provocation. Helium, by contrast, has a completely filled first energy level, 2 electrons held tightly by a 2-proton nucleus with no shielding at all. Its electrons are compact, close to the nucleus, and very difficult to remove. Helium is chemically inert. It does not react with anything under normal conditions. Its small size and tightly bound electrons make it one of the most unreactive elements in existence. The difference between cesium and helium, between one of the largest and one of the smallest atoms, between one of the most reactive and one of the most inert elements, comes entirely from quantum mechanics. From the number of protons in the nucleus, the number of electrons surrounding it, which energy levels those electrons fill, how much shielding the inner electrons provide, and how the balance between electromagnetic attraction and quantum confinement plays out at each level. None of this is arbitrary. None of it is accidental. The size of every atom in the periodic table is determined by the same handful of quantum rules, applied over and over again with increasing numbers of protons and electrons. The periodic table is not just a catalogue of elements. It is a map of quantum mechanics in action, a chart showing how the same fundamental principles produce a dazzling variety of atomic sizes and chemical behaviors, simply by changing the number of particles involved. Every atom has the size it has because quantum rules demand it. Electromagnetic attraction tries to pull electrons inward. The exclusion principle forces electrons into progressively higher and more extended orbitals. Shielding by inner electrons weakens the pull felt by outer electrons. Orbital penetration creates subtle energy differences that determine the filling order. And the uncertainty principle provides the irreducible confinement pressure that prevents any electron from collapsing into the nucleus. These effects working together, competing and cooperating across dozens of electrons and dozens of protons, produce the specific size of every atom in existence. And those sizes, as we are about to see, are not just numbers on a chart. They have consequences. Profound, tangible, physically real consequences that extend all the way from the invisible quantum world up to the objects you hold in your hands, the ground you walk on, the air you breathe, and the body you live in. So now we know where an atom gets its size. Electromagnetic attraction pulls electrons toward the nucleus. Quantum mechanics refuses to let them collapse all the way in. The uncertainty principle imposes a confinement cost that rises sharply as the electron is squeezed into a smaller space. The balance between these opposing pressures produces a stable electron cloud with a specific spatial extent. That extent is the size of the atom. Different elements have different sizes because of how many protons pull inward, how many electrons fill which energy levels, and how effectively inner electron shells shield outer electrons from the nuclear charge. But these are facts about individual atoms, objects so small that trillions of them could fit on the period at the end of a sentence. You do not experience individual atoms in your daily life. You experience tables, walls, rocks, water, air, your own body. Solid objects with definite shapes and volumes. Liquids that fill containers. Gases that expand to occupy rooms. The world you live in is built from atoms, but it operates at a scale vastly larger than any single atom. So the question becomes, how does the size of an atom, this quantum mechanical property of an invisibly tiny object, translate into the volume and structure and tangible physical reality of the macroscopic world around you? The answer is that atomic size determines almost everything about how matter behaves at the scales you can see and touch. The length of a chemical bond, the shape of a molecule, the spacing of atoms in a crystal, the hardness of a rock, the flexibility of a protein, the color of a gemstone, the conductivity of a wire, the reason your hand does not pass through a table, all of these trace back to the sizes of the atoms involved and the quantum rules that set those sizes. Start with chemical bonds. When two atoms come close together, their electron clouds begin to overlap. Depending on the atoms involved and the arrangement of their electrons, this overlap can produce an attractive interaction, a chemical bond that locks the two atoms together at a specific distance. The distance between the two nuclei in a bonded pair is called the bond length, and bond lengths are directly determined by atomic sizes. Consider a molecule of water. A water molecule consists of one oxygen atom bonded to two hydrogen atoms. The oxygen atom has 8 electrons arranged in the first and second energy levels. Hydrogen has 1 electron in the first level. When these atoms bond, the electron clouds of hydrogen and oxygen overlap and merge into shared molecular orbitals, regions where electrons are distributed across both atoms simultaneously. The distance between the oxygen nucleus and each hydrogen nucleus settles at about 96 picometers. This is the bond length. It is determined by the sizes of the oxygen and hydrogen electron clouds.
and by how those clouds rearrange when the bond forms.
If oxygen were a larger atom with a more extended electron cloud, the bond length would be longer. If hydrogen was smaller, the bond would be shorter. The specific bond length of 96 picometers is a direct consequence of the specific quantum mechanically determined sizes of oxygen and hydrogen atoms. Change the sizes and you change the molecule. Now extend this to larger structures. A molecule of DNA, the molecule that carries your genetic information, is an enormously complex structure containing billions of atoms. But every distance in that structure, every bond length, every angle between bonds, every gap between the two spiraling strands of the double helix is set by atomic sizes. The atoms in DNA are mainly hydrogen, carbon, nitrogen, oxygen, and phosphorus. Each of these has a specific atomic size determined by quantum mechanics. The bonds between them have specific lengths, determined by those sizes. The overall shape of the double helix, the width of the spiral, the spacing between the rungs of the genetic ladder, all of it follows from the sizes of the atoms and the geometry those sizes impose. If carbon atoms were 10% larger, DNA would have a different shape. Proteins would fold differently. The molecular machinery of life would operate differently, or might not operate at all. The precise sizes of a handful of common atoms, set by quantum rules operating at scales a billion times smaller than a cell, determine the architecture of every living thing on Earth. Bond lengths also determine the properties of solid materials. In a crystal of diamond, every carbon atom is bonded to 4 other carbon atoms in a rigid 3-dimensional network. The distance between neighboring carbon nuclei is about 154 picometers. This spacing, combined with the tetrahedral geometry imposed by carbon's 4 bonds, creates a structure that is exceptionally hard and rigid. Diamond is the hardest naturally occurring material on Earth. That hardness is a direct consequence of the short, strong bonds between carbon atoms, bonds whose length is set by carbon's atomic size. In a crystal of table salt, sodium chloride, sodium atoms and chlorine atoms are arranged in an alternating cubic pattern. Each sodium is surrounded by 6 chlorines, and each chlorine is surrounded by 6 sodiums. The spacing between neighboring sodium and chlorine nuclei is about 282 picometers. This specific distance depends on the sizes of sodium and chloride ions. Sodium, having lost its outermost electron, is much smaller than a neutral sodium atom. Chlorine, having gained an extra electron, is larger than a neutral chlorine atom. The bond distance in the crystal reflects these ionic sizes. In metals like iron, atoms are packed closely together in regular arrangements with their outermost electrons freed to roam throughout the material. The spacing between neighboring iron atoms is about 248 picometers. This spacing determines the density of iron, the speed of sound through it, its melting point, its strength, all traceable to the size of the iron atom and how iron atoms arrange themselves at that size. Every solid material you have ever touched has a specific density, a specific hardness, a specific set of mechanical properties. All of these emerge from how atoms of specific sizes pack together. Change the atomic sizes and you change every property of every material in existence. But there is a deeper question lurking here, one that goes beyond bond lengths and crystal structures. It is the question of why matter takes up space at all. Why does your hand not pass through a table? Why is a rock solid? Why does a chair support your weight? The atoms making up the table are overwhelmingly empty space inside. The atoms making up your hand are overwhelmingly empty space too. 2 clouds of almost nothing approaching each other. Why do they not simply drift through one another like 2 fog banks merging? The answer involves the same quantum mechanics that gives atoms their size, but applied to what happens when 2 atoms approach each other closely enough that their electron clouds begin to overlap. When 2 atoms come near each other, their electron clouds start to occupy the same region of space. The electrons from one atom encounter the electrons from the other, and here the Pauli exclusion principle becomes critically important. Remember, no two electrons can occupy the same quantum state. When the electron clouds of two atoms overlap, the electrons are forced into a shared quantum environment. If the low-energy states are already full, which they almost always are in atoms with many electrons, the incoming electrons cannot simply settle into those occupied states. They are excluded. They would need to jump into higher energy states to coexist in the same region. Jumping to higher energy states costs energy, a lot of energy. As the two atoms are pushed closer together, more and more of their electrons are forced into higher and higher energy configurations. This creates a powerful repulsive effect. The closer you try to push the atoms, the more energy you need to supply to promote all those electrons into unoccupied states. The resistance increases sharply with decreasing distance. It is not a gentle push. It is a wall of quantum mechanical resistance that becomes enormous very quickly. This is sometimes called Pauli repulsion or exchange repulsion, and it is fundamentally different from the electromagnetic repulsion between like charges. Electromagnetic repulsion between two negative charges pushes them apart because charges of the same sign repel. Pauli repulsion pushes atoms apart because the exclusion principle forbids their electrons from occupying the same quantum states. It is a purely quantum mechanical effect with no analogue in classical physics, and it is extraordinarily strong at short range. When you place your hand on a table, the atoms in your skin approach the atoms in the table's surface. Their electron clouds come close to overlapping, and the moment they do, Pauli repulsion kicks in with tremendous force, preventing the clouds from interpenetrating. The atoms in your hand cannot merge with the atoms in the table. They are held apart by the exclusion principle acting on their electrons. What you perceive as the solidity of the table, the resistance you feel when you press your palm against it, is the quantum mechanical refusal of electron clouds to occupy the same states. To grasp how essential this effect is, imagine for a moment that you could slowly turn it off. Imagine you had a dial that gradually weakened the exclusion principle, allowing electrons to share quantum states more and more freely. At first, you would notice nothing. The table would feel solid. Your hand would rest on its surface normally. But as you turned the dial further, the resistance would begin to soften. Your hand would press slightly into the surface, the way a finger presses into soft clay. The boundary between your skin and the table would start to blur. The atoms in your hand would begin to interpenetrate with the atoms in the wood, or metal, or glass, their electron clouds merging, their identities as separate objects dissolving. Turn the dial further, and solidity disappears entirely. Your hand passes through the table the way a shadow passes over a surface, without resistance, without contact. The table itself loses its rigidity. Its atoms, no longer held apart, begin to collapse into each other. The flat surface crumples, the legs fold. The entire structure compresses as atom after atom merges with its neighbours, the volumes that kept them distinct now gone. Everything in the room follows. Walls collapse inward, the floor gives way beneath you. Every solid object in the world simultaneously loses the property that made it solid. Without the exclusion principle, every electron cloud in the universe would be free to overlap with every other. Matter would have no volume, objects would have no boundaries. The physical world as you know it would simply cease to exist. This thought experiment is not science fiction. It is the logical consequence of removing a single quantum rule. Everything you have ever touched, every surface that has ever supported you, every wall that has ever enclosed you, exists because electrons obey the Pauli exclusion principle. That principle, combined with the finite size of electron clouds set by the uncertainty principle, is what makes the physical world solid. It is what gives matter volume. Your hand does not pass through the table because electrons are fermions, particles that obey the exclusion principle. If electrons were bosons, particles that can pile into the same quantum state without restriction,
matter as we know it would not exist. Atoms would not resist interpenetration. Solids would not be solid. Your hand would pass through the table. You would fall through the floor. Nothing would hold anything up. The volume of every object you have ever seen, the space it occupies, the room it takes up, exists because electron clouds have a finite size set by quantum mechanics, and because the exclusion principle prevents those clouds from being compressed into each other. Without quantum mechanics, there is no atomic size. Without the exclusion principle, there is no material volume. The physical world, in the most literal sense, is held open by quantum rules operating at scales far too small to see. There is also a contribution from simple electromagnetic repulsion. Electron clouds are negatively charged. When two negatively charged clouds approach, they repel each other electrically. This electromagnetic repulsion adds to the quantum mechanical resistance, reinforcing the effect. The two mechanisms work together: electromagnetic repulsion pushing the clouds apart, and Pauli repulsion preventing them from merging, creating the impenetrable barrier that we experience as the solidity of matter. The strength of this barrier depends on atomic size. Atoms with large electron clouds begin repelling at greater distances. Atoms with small, compact clouds allow closer approach before repulsion becomes significant. This is why different materials have different densities. In a block of lead, the atoms are relatively large and packed together at spacings set by their electron cloud sizes. Lead is dense because lead atoms are heavy, but the spacing between them is also influenced by their atomic and ionic radii. In a block of lithium, one of the lightest metals, atoms are arranged at spacings set by lithium's smaller size. Lithium is much less dense than lead, partly because lithium atoms are lighter, and partly because the interatomic distances reflect different atomic sizes. But atoms do not only push each other away, they also attract each other, even when they are not sharing electrons in a chemical bond. And here, atomic size plays yet another role, one that shapes everyday phenomena most people never think to connect to quantum mechanics. When two atoms or molecules come close to each other, even if they have no chemical bond and no permanent electric charge, they still experience a weak mutual attraction. This is called the van der Waals interaction, and it arises from a subtle quantum effect involving the electron clouds themselves. At any given instant, the electrons in an atom are not perfectly symmetrically distributed. The cloud fluctuates. For a fleeting moment, there might be slightly more electron density on one side of the atom than the other. This creates a tiny, temporary electric imbalance, a momentary dipole that appears and vanishes almost instantly. But while it exists, it influences the electron cloud of a neighboring atom, inducing a complementary imbalance in that atom. The two temporary dipoles attract each other.
The interaction is extraordinarily weak and extremely short-lived, but it is always present, and when summed over trillions of atoms, it adds up. Atomic size directly controls the strength of this effect. Larger atoms have more diffuse, more loosely held electron clouds. Those clouds are more easily distorted, more polarizable, which means the temporary dipoles are larger and the van der Waals attraction is stronger. Small atoms with tight, compact clouds are harder to distort. Their van der Waals forces are weaker. This explains why the noble gases, despite having no chemical bonds at all, can still be cooled into liquids. Helium, the smallest noble gas, has the weakest van der Waals forces and the lowest boiling point of any substance, just 4.2 degrees above absolute zero. Neon is a bit larger and boils at a higher temperature. Argon, larger still, boils at a higher temperature yet. Krypton and xenon, progressively larger, have progressively higher boiling points. The trend is clean and direct. Bigger atoms, more polarizable electron clouds, stronger van der Waals forces,
higher boiling points. Atomic size, set by quantum mechanics, determines when these substances transition from gas to liquid. The same effect explains why geckos can walk up glass walls. The pads on a gecko's feet are covered in millions of microscopic hair-like structures. Each one comes into extremely close contact with the surface, close enough for van der Waals forces between the atoms in the gecko's foot and the atoms in the glass to generate a measurable adhesive force. Individually, each contact point is negligibly weak, but summed across millions of contact points, the total force is enough to support the animal's weight against gravity. A gecko clings to a wall because of quantum mechanical fluctuations in electron clouds operating at the atomic scale. Atomic size also governs chemical reactivity in ways that shape the entire material world. Large atoms with loosely held outer electrons tend to be highly reactive. Cesium, one of the largest atoms, reacts violently with water, igniting on contact. Its outermost electron is so far from the nucleus, so weakly held, that it takes almost no provocation to tear it away. Small atoms with tightly held electrons tend to be far less reactive. Helium, with its tiny, compact, completely filled electron cloud, does not react with anything under normal conditions. Neon, argon, and the other noble gases are similarly inert, their full outer shells creating electron clouds that are symmetric, compact, and uninterested in bonding. Between these extremes lies the rich middle ground where chemistry happens. Carbon, with its 4 outer electrons in the second energy level, is perfectly suited to forming 4 strong bonds with other atoms. Its atomic size places it in a sweet spot where the bonds are short enough to be strong, but the atom is versatile enough to bond in many different geometric arrangements. This is why carbon is the backbone of organic chemistry. Virtually every molecule in your body, every protein, every strand of DNA, every sugar, every fat, is built on a framework of carbon atoms bonded together and to hydrogen, oxygen, nitrogen, and a few other elements. Carbon's atomic size, set by quantum mechanics, makes this molecular versatility possible. Oxygen's atomic size makes it one of the most effective electron acceptors in chemistry. Its electron cloud is compact enough that it holds electrons tightly, making oxygen electronegative, hungry for other atoms' electrons. This is why oxygen is so central to combustion, to respiration, to corrosion, to the chemistry of water. Hydrogen's small size and single electron make it the simplest and most flexible bonding partner, capable of attaching to almost anything. Nitrogen's intermediate size and its 3 available bonding electrons make it essential for proteins and DNA.
The sizes of these atoms, carbon, hydrogen, oxygen, nitrogen, are not just numbers. They are the architectural constraints of life. They determine bond lengths, which determine molecular shapes, which determine how proteins fold, which determines how enzymes work, which determines how every chemical reaction in your body proceeds. The chain of causation runs from quantum mechanics at the subatomic scale all the way up to the functioning of living organisms. Atomic size also explains the behavior of gases. In a gas, atoms or molecules are far apart, separated by distances much larger than their own sizes. They move freely, bouncing off each other and off the walls of their container. The size of the atoms determines how closely 2 gas particles can approach during a collision. Larger atoms have a bigger effective collision diameter. This affects how often collisions occur, which in turn affects properties like viscosity and thermal conductivity. Even in the diffuse, freely moving world of gases, atomic size matters. In liquids, atoms or molecules are close together, but not locked into fixed positions. They slide past each other, constantly rearranging. The size of the molecules determines how tightly they can pack, which affects the liquid's density. It also affects surface tension, the tendency of a liquid surface to minimize its area. Water's remarkable surface tension, strong enough to support small insects walking on its surface, arises from hydrogen bonds between water molecules, bonds whose geometry and strength are set by the sizes of oxygen and hydrogen atoms. The electrical properties of materials are also rooted in atomic size. In metals, the outermost electrons of each atom are so loosely bound that they detach and form a shared sea of mobile electrons flowing through the material. This is what makes metals conduct electricity. The atoms that form the best conductors, copper, silver, gold, have outer electrons in energy levels and orbital configurations that make those electrons easy to liberate. The atomic sizes and electron configurations of these elements determine how many free electrons are available and how easily they move. In insulators like diamond or glass, the electrons are tightly bound in compact orbitals, locked into strong bonds between atoms, unable to move freely. The atomic sizes and bond geometries create an electronic structure with no free electrons available for conduction. The material resists the flow of electricity. In semiconductors like silicon, the situation is intermediate. The electrons are bound, but not as tightly as in insulators. A small input of energy, heat or light, can free some electrons and allow limited conduction. The exact energy required depends on the atomic size and bonding geometry of silicon atoms in the crystal. This is the foundation of all modern electronics. Every computer, every phone, every digital device you have ever used operates because silicon atoms have a specific size that creates a specific crystal structure that produces a specific electronic behavior. Quantum mechanics at the atomic scale enables the technology that defines modern civilization. Let me step even further back and consider the broadest possible perspective. Every object you have ever seen has a volume. Every chair, every mountain, every ocean, every planet. Volume means spatial extent. It means taking up room. And all of that volume, every cubic centimeter of every object in the universe, exists because atoms have a finite size. If you removed quantum mechanics from the universe, if the uncertainty principle did not exist, electrons would spiral into the nucleus in a trillionth of a second. Every atom would collapse to nuclear dimensions. All of the matter in your body would compress down to a speck far smaller than a grain of sand. All the matter on Earth would compress to a sphere a few hundred meters across. There would be no molecules, no crystals, no liquids, no gases, no solid ground, no oceans, no atmosphere. Everything would be a super-dense lump of nuclear matter with no chemistry, no structure, and certainly no life. The physical universe you inhabit, the one with mountains and rivers and cities and stars and people, exists only because quantum mechanics gives electrons a minimum spread around the nucleus. That spread creates atomic volume. Atomic volume creates molecular structure. Molecular structure creates materials. Materials create the world. The chain is unbroken, and it starts with quantum rules that operate at scales 10 billion times smaller than anything you can see with your naked eye. And everything along this chain is set by a small handful of fundamental constants. Planck's constant, which determines the scale of quantum effects. The electron mass, which determines how much kinetic energy confinement costs. The electron charge, which determines the strength of electromagnetic attraction. The speed of light, which enters through the fine structure constant. From these few numbers, you can derive the size of a hydrogen atom. From atomic sizes, you can predict bond lengths. From bond lengths, you can model molecular shapes. From molecular shapes, you can understand materials. From materials, you can understand the physical world. If any of these constants were different, atomic sizes would change. If Planck's constant were larger, the confinement cost would be greater. Electrons would spread farther from the nucleus, and atoms would be bigger. Molecules would be larger. Materials would be less dense. Chemistry would be different. Life, if it could exist at all, would look nothing like what we know. If the electron charge was stronger, electromagnetic attraction would pull electrons closer to the nucleus. Atoms would be smaller. Bonds would be shorter and stronger. Materials would be denser and harder. Chemistry would shift in ways that might make complex molecules impossible. If the electron were heavier, it would cost less kinetic energy to confine it to a small space, because heavier particles carry less kinetic energy at any given momentum. Atoms would be smaller. If the electron were lighter, atoms would be larger. The specific mass of the electron, a number that as far as we know has no deeper explanation, directly determines how big atoms are, and therefore how big everything is. This is one of the most profound realizations in all of science. The size of every object in the universe, from a grain of dust to a star, is ultimately traceable to quantum mechanical rules and a few fundamental constants. The world is not arbitrary, it is not random. Its structure is dictated from the bottom up by the physics of the very small. The fact that you are about 1 3/4 meters tall and not 100 times taller or 1,000 times shorter. The fact that rocks are hard and water is wet and air is invisible. The fact that the periodic table has the structure it does and chemistry works the way it does. All of it connects back to the quantum mechanical origin of atomic size. When you reach out and pick up a glass of water, you are interacting with trillions upon trillions of atoms, each one held open to its specific size by the quantum balance between electromagnetic attraction and confinement energy. The glass is solid because the electron clouds of its silicon and oxygen atoms resist compression through the exclusion principle. The water inside is liquid because its hydrogen and oxygen atoms form molecules whose size and shape allow them to slide past each other while remaining loosely connected through hydrogen bonds. Your fingers grip the glass because the atoms in your skin and the atoms in the glass push against each other electromagnetically and quantum mechanically, refusing to interpenetrate. Every aspect of this mundane, everyday action, picking up a glass, is governed by atomic size and the quantum rules that determine it. You are, in a very real and physical sense, a structure built from quantum mechanics. Your body is a collection of atoms held open by the uncertainty principle, locked into molecular arrangements by chemical bonds whose lengths are set by electron cloud sizes, organized into cells and tissues and organs whose structures depend on the geometry of those molecules. You exist at the scale you do because electrons have the mass they do, because Planck's constant has the value it does, because the electromagnetic force has the strength it does. These constants, woven together through the mathematics of quantum mechanics, produce the atomic sizes from which everything is built. So, where does an atom get its size from? Not from a wall, not from a shell, not from any hard boundary at its edge. An atom gets its size from the quantum nature of its electrons, from the electromagnetic force pulling inward and the uncertainty principle pushing outward, from energy levels and orbitals and the exclusion principle and shielding and penetration and all the subtle quantum effects that determine how electrons arrange themselves around a nucleus. The size of an atom is a quantum mechanical equilibrium, a balance point set by the deepest laws of nature, encoded in a few fundamental constants, and manifested in every speck of matter in the universe. And that quantum equilibrium, reached inside every atom in existence, is the reason the physical world has volume. It is the reason matter takes up space. It is the reason you can stand on solid ground, hold objects in your hands, and look up at a night sky full of stars whose light was emitted by atoms whose sizes obey exactly the same quantum rules as the atoms in your eyes. There is something quietly staggering about this. You live your entire life surrounded by solid objects, trusting surfaces to hold you, relying on matter to behave in predictable ways, never once questioning why the floor supports your weight or why a wall blocks your path. These seem like the most obvious, least remarkable features of existence.
Of course, the floor is solid. Of course, objects have volume. Of course, your hand cannot pass through a table. What else would you expect? But now you know what holds it all up. Not substance, not solidity in any classical sense, not little hard balls packed tightly together. What holds it up is a quantum rule about probability clouds, a principle about how electrons are forbidden from sharing the same state, a balance between an electromagnetic force pulling inward and a confinement energy pushing outward. These invisible, intangible, deeply abstract effects have been quietly holding the universe open since the first atoms formed in the minutes after the Big Bang, billions of years before any conscious being existed to wonder why matter takes up space. Every chair that has ever supported someone, every bridge that has ever spanned a river, every bone that has ever held a body upright, every grain of sand on every beach on every continent. All of it, all of that structure and solidity and volume, traces back to quantum mechanics operating inside atoms at scales no human eye will ever see. The universe is built from the quantum mechanics of the very small. And the very small, it turns out, is where everything begins.